Alright, so let's take a look at today's lesson. Today's lesson is on derivatives and differentiability. Let's think a little bit about yesterday's lesson. On yesterday's lesson, we kind of really were introduced to some topics that have to do with derivatives, like the normal line and the tangent line and the secant line. So we just really kind of touched on those and talked about what those were. We're going a little bit farther into derivatives today. We're going to look at finding derivatives, the different ways that they're represented, and we're also going to talk about differentiability. So that's kind of what our lesson is on today. So let's take a look at the different ways that you can represent a derivative. You can represent a derivative analytically, which actually, okay, that's my favorite way. I love algebra. It's like one of my favorite things. So representing it like with an equation, you can write the equation of a derivative, you can find the equation of a derivative or use it. We are familiar with these now. We talked about these at length. Definition of the derivative, alternative form of the definition of the derivative. So those are an analytic representation of the derivative. This word right here, pretty important, different quotient. I have it underlined. Reason being is that the difference quotient, that verbiage can appear on the AP test or on other types of things, and we need to know what it means, and it will, for us, appear on a formula quiz. So a difference quotient, what we're really referring to is this definition of the derivative. So if I write on the formula quiz difference quotient equals, then you would write the definition of the derivative. It's like a vocabulary word. You need to know that vocabulary word. If you wrote the alternative form, I would be okay with that too, because it also is a quotient and it's a difference. So either one of those would be fine when I put this word on the formula quiz, because you will see it at some point during the year. So difference quotient is simply the definition of the derivative or the alternative form. So next, let's look at a different way to represent a derivative, and that's with a graph. So we can represent a derivative with a graph. We talked about that a little yesterday. In this particular case, we are looking at a tangent line. And remember, we talked about the slope of the tangent line is the value of the derivative at the particular point of tangency. So that's one way to represent a derivative on a graph, is by the tangent line and thinking about the slope of the tangent line. There are other ways to represent a derivative on a graph, like actually graphing the equation of the derivative, but this is the one that we have highlighted right here, and that is the slope of the tangent line, is the value of the derivative at this particular point of tangency. The third way to represent a derivative is numerically. This is a little bit more of a formal way. We don't really use the numeric technique for derivatives very often. I mean, some, but not terribly often. The concept here is that the derivative is a point that's the limit of the slopes of the secant lines or the limit of the difference quotient. And it's a formal way to think about a derivative as a limit. So what would that look like? So in this particular case right here, we have the tangent line, but what this is talking about is, secant line. So let's say we have a secant line right here. And then let's say we pull it in a little bit closer. And then we keep pulling it in closer and closer and closer until we actually take the limit, and that would give us the actual number. That's the formal concept of a derivative. Now, we don't really get into the formal concept very much, but that's what this is talking about. Okay, and so that is the numeric way to represent a derivative. All right, so let's, one other concept right here is a one-sided derivative. We know we have one-sided limits. Well, we've looked at those before. We have one-sided continuity, right? We talked about continuous from the left, continuous from the right. We have that. We also have one-sided derivatives. We're really not going to use them that much. They're most used with piecewise functions. That's when we use them, is with piecewise functions. And we will use a one-sided derivative here when we're working on this particular problem. So I just kind of want you to know they exist. We use them from time to time, mostly with piecewise functions. So the instructions tell us to use the alternative form of the definition of the derivative to find the derivative if it exists. Okay, so let's do that. Now we're still playing with the limit, for definition. Next week we're going to learn all the rules, and we're going to kind of move away from the limits. And I know you're going to be really sad. I'm going to be really sad, but that's the way it is. We're just going to learn actual rules to find derivatives instead of using this technique. But we're still get to use it. So let's do that. So we have the limit. We're using this particular one. They want us to use the alternative form. The limit as x approaches, our c value is 9, as x approaches 9. And we have a fraction. It tells us to put the function first. The function is square root of x. Then it tells us to subtract the function at the c value. So I'm going to subtract the function at the c value. That's what that is. And in the denominator, we're supposed to put x minus c. We are just filling in the formula. That's what we're doing. Once we have the formula filled in, it's simply a limit that we have to solve. So let's do that. So we know square root of 9 is 3, so we get square root of x minus 3 over x minus 9. So thinking about different techniques to solve this limit, I would multiply by the conjugate of the numerator. That's what I would try. So let's do that. So square root of x plus, it's not covered, square root of x by itself, and then plus 3 over square root of x plus 3. All right, so let's rewrite it. So we love conjugates, right? Because the middle part just falls away. So square root of x times square root of x is x. The outside inside portion just disappears. And then the last times the last, negative 3 times 3 is a negative 9. And notice how I'm not distributing in the denominator, because if I do, I miss my little gift right there, right? The little present that we see. We see that the x minus 9s go away. Gone. And so we basically can take the limit now. We can substitute the 9 in. And so when I do that, I substitute the 9 in. I have 1 over the square root of 9 plus 3, or, so f prime of 9 is going to equal 1 over 6. And that's what we were doing the whole time. This is f prime of 9. If you want to put the derivative notation outside there. So f prime of 9 is the first derivative of that function at 9. So basically the derivative exists at 9. That's what it's telling us. And we know the value. The value is 1/6. Okay, is that okay? All right. On this next one, we need to work with the piecewise function. Let me get a little bit of room over here. Okay. So we're familiar with piecewise functions. We've worked with them before. We know that if we're looking for continuity, if it's continuous, what we do, we would take the 1 and we would put it in here, right, and get a 3. We take the 1 and put it in here, get a 3. We're like, yay, it's continuous, right? That's what we would do. So when we do derivatives, and of course they want the derivative at 1, right? They're not going to make it easy for us. They want the derivative at 1. So when they do derivatives, we actually have to do one-sided derivatives here. We have to do the derivative from the left and from the right. And what we want is for the values to be the same. If we do both of the derivatives, the one-sided derivatives, and we get the same value, then the derivative exists there, and that's the number. But if we work the one-sided limits and we don't get the same value, then the derivative doesn't exist at 1. Okay, you with me? That's how we determine whether it exists or not, is we have to do the one-sided limits. All right, so let's do that. So let's do f prime of 1. Let's go from the left first. So the limit as x goes to 1 from the left, and we're going to use this formula right here. So recall we put the function in first. So x squared plus 2 minus, I'm going to substitute a 1 into this function and get 3 all over x minus 1. We okay with that? I'm just substituting into the alternative form. Now we're going to clean it up and work with it. So we have, so this is f prime of 1. It's really from the left. limit x goes to 1 from the left. So 2 minus 3 is negative 1, so I get x squared minus 1 over x minus 1. So we've been solving limits for a few weeks now, right? We're pretty comfortable. We know we're going to factor the numerator. We're going to be able to cancel out. And that's what's going to work for us. So f prime of 1 from the left, limit x goes to 1 from the left, so we got x plus 1, x minus 1 over x minus 1. Beautifully, that goes away. Now we can take the limit, just substitute the 1 in there, and I'm going to get a value of 2. Okay, so we'll get a value of 2. This limit is going to be 2. So the derivative from the left side is 2. All right, now let's do the derivative from the right side. So we have, and let's kind of clean this up a bit. There we go. All right, so we're going to do f prime of 1, and this time we're going to do from the right. We're going to come from the right. And this particular function from the right is 3x. So I'm going to put that with the f of x, so 3x, then minus, I'm going to put the function value in, put a 1 in there, and I get 3 over x minus 1. That's the limit that I'm having to solve. Okay, so let's simplify that. So the limit as x goes to 1 from the right, I'm going to factor 3 out. Very nice, very nice. Goes away. So that limit value happens to be 3. Happens to be a 3. So what does that tell us about the derivative at 1 for that piecewise function? Does it exist or not? It doesn't. It doesn't exist. So the derivative at 1, so f prime of 1 is d and e, does not exist. Which reminds me, on the quiz that I just passed back to you, some of us got a limit that was d and e, and when we do, remember that we have to prove that by doing the one-sided limits. I think most of us did, but there were a few of us that forgot to do that. All right, how's that part? We okay so far? All right, so that's talking about derivatives. Let's now talk about differentiability. So let's go to the other slide. Another thing that, gosh, isn't it so fun? We're just like, I just keep adding things and all the stuff we get to remember. You're probably saying, that's not enough, we need more. I know, we're getting there fast enough, right? So this is differentiability. We're going to learn when to determine whether a function is differentiable or not. Really, there are only 3 reasons why we would be non-differentiable. Okay, yes, I put this on the formula quiz. I usually ask it, what are 2 of the reasons why a function, or sometimes 3, what are the 3 reasons why a function would be non-differentiable? And every year I have students write corner as one reason and cusp as the second reason. Okay, that's not 2 different reasons. This is the same concept. So I have it labeled, it's right here, corner or cusp, number 1. That's the same thing. So corner or cusp, what is that? Well, here's a corner, right? It's a sharp turn in the graph, and a cusp looks like this. All right, so at that location, at the corner or the cusp, the derivative does not exist. It's continuous there, but the derivative doesn't exist. So let's talk about why. If we think about the formal definition where we, have all these secants and we're getting closer and closer on either side, these are not going to have the same limit. If we were to do that, that's a formal way to think about it. A more informal way to think about it is, well, if I'm going to draw a tangent line there, where would I put it? Well, it looks like a whole lot of different places I could put it, right? I could put the tangent line like that. That looks pretty good. What about like, that? That looks like a pretty good tangent, right? I mean, how would we write our tangent? So, logically, we'd think that's impossible. We can't put a tangent line there. So, at a corner or a cusp, the derivative is not defined. The second reason would be discontinuity. Well, that kind of makes sense. If there's no point there, I can't have a derivative there. Didn't we talk about the value of the derivative at a point is the value of the tangent line at that point? Well, if I don't even have a point there, how am I going to put a derivative there, right? So that makes sense. There are no derivative values at a discontinuity. So that's the second reason. The third reason is a vertical tangent. Maybe not so obvious. I think these pretty well logically make sense why I wouldn't have a derivative in either of these places. This one might be a little bit of a stretch, but let's talk about the concept. So a vertical tangent. All right. So we know that the value of the derivative is equal to the slope of the tangent line at that point. Right? They're equal. We just talked about that. So what is the slope of a tangent line, a vertical tangent line? It's undefined, right? There is no slope. It's an undefined slope. So that would make sense if this tangent line is a vertical one, its slope is undefined, therefore the derivative there will also be undefined. So that kind of makes sense, but maybe not as obvious as these other two. So those are the three reasons why a function would not be differentiable at a point. So we have one example to work through. We have this graph right here, and it says state the domain where the graphs are differentiable. Okay, so that's one question. Continuous but not differentiable. That's the second question. And neither continuous nor differentiable. That's the third. So we have three different questions here. So the first one, differentiable. Well, okay, we're looking along here. We're going to start at -2. I'm writing in interval notation. It's domain. These are not points that I'm writing. These are x values. And I can't include -2. There is a one-sided derivative that exists there, but not the full derivative. Okay, they're not asking about one-sided. They're asking about the derivative. So I'm not going to include -2. So I move along here, and I see my first problem area is this one, -1. That is a corner. The derivative does not exist at a corner. So I've got to stop at -1. Okay, I'm going to put a comma, or you could put a U. It's up to you. So now we pick up from -1, and let's see where we're going. Here's our next problem is at 0. There's a discontinuity there. So no derivative there. All right, so then we will pick up on the other side of 0, and we'll go to 2. I can't include 2 because there's a hole. There's no derivative at a hole. And then I will finish out from 2 to 3, again not including 3 because there's nothing on the right side of 3. It just stops. And so that's number 1, differentiable. Number 2, continuous but not differentiable. It looks like just right here at -1, right? That's a corner. It's continuous. So at x equals -1, that's a problem. It's continuous but not differentiable. And the last one is, let's see, neither continuous nor differentiable. Well, if it's not continuous, we know it's not differentiable, right? Those go hand in hand. But that's okay. Let's take a look. So, all right. We're not continuous at 0. That would be a problem. There will be no derivative there. So x equals 0. Where else? We're not continuous at 2. That's a problem. So there will be no derivative there either. And that is it on that problem. How is that? Okay.